And maybe I can start with a little story. So somehow I first basically met him as a speaker when I was in the audience as a graduate student, and somehow it maybe took a while before I realized what an eminent figure he actually is, because he wasn't the kind of person who would make a number out of that himself. A little bit to the contrary, he in his talk he might say something like, "This goes in this and this way," or "also my collaborators have been telling me." And so somehow the first impression that one could get was maybe that he was perhaps some kind of a hang-around fellow in a collaboration, and it maybe took a while to realize that actually the situation might have been the complete opposite. Okay, but now to the actual talk. So somehow the basic question that I'm studying in the talk is to understand, we are given some operator T, so or maybe let's say we are given some formula and we would like to ask whether this formula in a reasonable sense defines an operator, a bounded linear one, between some LP spaces and possibly with different measures and even different exponents. So of course maybe I take the freedom of writing one formula which everyone knows, of course, that what it means is that we should check an inequality like this for all functions in the prospective domain. Of course, we also immediately realize that there is quite a bit to check if you start doing it one function by time. So somehow, preferably, you would like to have some conditions that, let's say, for some particular classes of operators, you would only need to check something a little bit simpler. So the hope is that it would be enough to check something slightly more feasible, such as assuming that these are measures on, let's say, Rn. You have the notion of cubes. Maybe instead of all functions, you would like to plug in only the indicator functions of cubes. So this is an obviously necessary condition. If the final result is going to be true, this is an obvious necessary condition. And likewise, let's say at least, and this is the restriction that I will have throughout this talk, except for a couple of remarks to the contrary. So if we are in the reflexive region, if we hope to have a linear operator in the end, then the linear operator should have an adjoint, and the adjoint should also satisfy the corresponding estimate between the dual spaces. So then you can write down another necessary condition. You can guess how it goes on. So these are some things that are obviously necessary, and now the hope is that maybe in some cases it would be sufficient as well. Now it's clear that you can quickly cook up some examples which show that it cannot be. So once again, this is not about general operator theory. Clearly, certainly it's not sufficient for an arbitrary operator that you can cook up, but maybe for some special classes. And in the talk, I basically have two parts. So this is the 0th one, and I have still 2 to go. So I will consider two kinds of operators. Both of them are sort of like dyadic models of some let's say, more serious operators of harmonic analysis. So the first type of operators that I consider are the Haar multipliers. So a little, like a background to this is that recall that we have the, let's say we could be on just the real line or even the unit interval. The Haar functions, which look like this, appropriately normalized in L2. They form an orthonormal basis, so you can expand any function like this, and then the Haar multiplier that you would like to consider is that you just multiply the expansion by some constants. And because it's orthonormal, so it's a bounded let's say if this is a bounded sequence, it's a bounded operator in L2. Actually, because this one is an unconditional decomposition in LP, it's also a bounded operator in LP, unweighted. But now what we really want to consider is, again, the two-weight situation. So the actual question here so we apply it to f times a measure, so it's somehow sufficiently clear, it should be clear what it means. So if I put hi paired with f times a measure, I mean that I integrate hi times f with respect to the measure. Notice that I put the same measure here in the domain of the function and here inside the operator. I could do even slightly more general to start with, but without essential loss of generality, I can always reduce to this situation that the same measure appears in this and this position, but here is a possibly different measure. Okay. So what is known about the situation? There are some answers known. Especially in the case that P is equal to Q is equal to 2. So this is the Hilbertian situation. So I can provide a couple of answers. First, it turns out, so there are the Haar functions. They take positive and negative values. So this is somehow it's a question involving cancellation. You can somehow make it slightly less cancellative if instead of considering a fixed sequence of multipliers, you somehow consider all possible signs of the multipliers and you ask for a uniform inequality. And in this case, so let your epsilon be so epsilon is a sequence of epsilon i's. So you have so for a fixed alpha, for a fixed pair of measures, you have the uniform estimate over all signs if and only if you have the corresponding uniform testing conditions and the corresponding uniform dual testing conditions. So this is a result of Nazarov, Fedor Nazarov, Sergei Treil, Alexander Wolberg. I think this same paper was also mentioned in the previous talk, and I will mention it again a little bit later on. And actually, almost 10 years later, they managed to get rid of the same without this one. So this is a result by the same trio of people about 10 years later. But notice that everything here is in the Hilbertian situation, and this, of course, you can any Banach space person realizes that one can derive some benefit out of this restriction. So now the question is, can you do something? Can you say something about these operators for other values of P and Q away from the Hilbert space case? And well, it's not much available about this one, and the reason is that there is a counterexample which kind of indicates that you cannot, or actually which says that you cannot have the same thing. You cannot have something as nice as here. So actually now this is about P equal to Q and not equal to 2. And so there is so if we are in this situation, then, well, actually maybe I will, let me do it in a more efficient way. I exploit the text that I have already written, and I use a different color. So now in the red case, this implication fails. Of course, it's clear that the other implication is of course true, because it just amounts to specializing to the case that you take the indicator function in place of f. But this condition is not enough to get this one, even in the uniform version, and then also not in this one. So, well, you can easily figure out that somehow having it for a fixed sequence, the positive result for a fixed sequence is stronger than the positive result with the supremum. So therefore a counterexample to the version with the supremum is also a counterexample to this version. So this is so what I wrote in red is, or maybe is it pink? So this is also by Fedya Nazarov. This is actually, it's an unpublished, untitled, and undated manuscript, which I happened to get my hands onto via some third-hand parties, but but nevertheless, there is such a counterexample, and I have more or less, it's written quite condensedly, but I have more or less checked it for myself that this is the case. So it's a rather, could be interesting to understand it in a more explicit way. So somehow, so the counterexample is based on this, on the method of, well, like many results of these people, on the method of Bellman functions, which is also connected somehow with a prehistory of this goes back to the work of Burkholder on the unconditionality constant of the Haar system. So basically what Burkholder did is that he said that the unconditionality of the Haar system is equivalent to the existence of a function with certain convexity properties, and then he proved that such a function exists, and therefore you get the result. Well, here it's somehow, it's the same philosophy, but but used in a different way, in the sense, again, he shows that, okay, if the implication was true, then there would exist a function with a function of 5 real variables, which has certain convexity and concavity properties with respect to the different groups of the variables. After some computation, basically elementary calculus, but kind of you need to know what to do. you realize that these convexity and concavity properties are self-contradictory, such a function cannot exist, therefore the inequality cannot be true. But so there is no, so somehow it's a counterexample without saying explicitly what are the functions, what are the measures which produce you the counterexample. Okay, but probably because of the, I mean, I guess many experts in the area knew about this manuscript, and therefore not much was done about p not equal to 2. So now, why am I talking about this then? So the point is that, of course, it says that you cannot, so this implication, no, there is no way that I could, so putting p here, no way that I could have this implication. However, of course, it doesn't say that I couldn't have any characterization. Maybe I could have some other characterization. And if now that I know that this characterization is not enough, or I mean this condition is not enough to imply this one, if there is going to be a characterization, it has to be in terms of a condition which is something stronger than this one. Okay, now if you have been following the talks starting from the morning, so there might be an idea in the back of your mind that what you need more in the LP to restore results that are true in L2. So in place of boundedness, you should have R-boundedness. So this is an idea that I gave to my student Emil Vuorinen, and he has his first preprint in the archive in December. And okay, maybe as a little prelude to this, I should recall something that was also already mentioned in the morning. So the theorem of Bailey, Marcinkiewicz, and Sigmund. So if you have the LP boundedness, and I'm not sure if it was stated for 2 different measures, but certainly with the same proof you can do that. Then you also have the little L2 valued extension. So therefore, what can we do? Okay. Actually, yeah, I should. So maybe I write this sigma inside, and also here. And I can do, of course, I can do the same thing for the adjoint. Okay, maybe it's useful to write it once. Okay, it appeared in the morning, but maybe I nevertheless write it down. So the conclusion of this implication means that if the operator is going to be bounded, then it's also bounded in this vector valued sense. And now, to derive an obvious necessary condition, I can, instead of just plugging in special functions in the original inequality, I substitute special testing functions into the vector valued inequality. So I take for Fi a constant times the indicator of any cube. And similarly here. So Fi, I just substitute a constant. And in a similar way, I can derive the necessity of a corresponding dual inequality. So this is a different set of necessary conditions for the boundedness. which is stronger than just the kind of conditions here. And then it turned out that this kind of the R-bounded version of the testing conditions, conversely, is enough to go back to the original one. So this was done by my student. So therefore now all of these are equivalent, and in particular this two-weight inequality is characterized by these R-boundedness style testing conditions. Okay, so now it maybe remains to be, so this is fairly recent, it maybe remains to be seen whether such a characterization is useful for any further developments, but in any case it shows that somehow it has broken the barrier of being able to do only the Hilbertian case here, so at least you can do some characterization also for P and Q different than 2. Okay, so that's the first part of the talk, and then I will discuss another class of operators, which is a little bit connected to the previous talk of Professor Verbitsky. Okay, so the second part is about positive dyadic operators. And here, so I again keep using the letter T for my operator, so T of F, or maybe I immediately put the measure inside. So this means that I take a sum over all dyadic cubes. I have some positive coefficients. Then I have the integral of my function. And then I place this value on the Q. So I multiply by the indicator. So this is an explicit. And so here lambda Q is bigger than or equal to 0. So this is a formula. And now the question is, under what conditions can I have the boundedness of these operators? Maybe I should also introduce the truncation with the subscript Q naught. This is something slightly, so when everything is positive, this is something slightly smaller. So notice that this is a little bit smaller than putting the indicator inside. Because if I put the indicator in, I get all cubes like this, but I also get a certain contribution from the cubes that contain Q naught. But this is kind of like a convenient truncation when dealing with these positive operators. So now it's not about cancellation. Everything is positive. So in a sense, it should be an order of magnitude easier. And indeed, this situation is somehow it was already understood before, but I kind of want to put some perhaps R-boundedness kind of flavor into this question as well. So again, okay, I'm not rewriting. So the question is exactly the same as before. When is the operator bounded? Maybe I remove the alpha from here so I can reuse the same. But now here the interesting thing is that we have kind of like a dichotomy in terms of the known results. Basically, all the P's in the reflexive range are understood, but somehow they are understood in a little bit different terms. So first there is the case that P is smaller than or equal to Q, smaller than infinity. And in this case, the boundedness, as I have written there, Yeah, maybe actually maybe it was yeah, well, doesn't matter. Yeah, so I can. So this is like a slightly. I'm not really using these special truncations in any essential way. I could have just stated the usual testing conditions. Maybe I actually forget about the truncations. I don't really need it. So it's equivalent to the testing condition and the dual testing condition. Maybe it's fair to mention a little bit of the history. So there is under some additional conditions on the coefficients. So let me just say special lambda q's. This goes back to Eric Sawyer in the 80s, maybe 1988. And then for arbitrary lambdas, but again under the restriction that P is equal to Q is equal to 2. So this is the same paper of Nazarov, Trail and Wahlberg, 1999. And then as stated, it's by Michael Lacey, Eric Sawyer, and Ignacio Uriarte Tuero, 2008. And it seems to me that the original proof has remained well, okay, it's in the archive, but it seems that it hasn't really been published in a journal, because somehow once they proved it, then several simplifications of the proof have appeared by quite a few different authors, but they were really still the first ones to obtain the inequality in the generality as stated. So in principle, everything is known. And also so let me write down the other case. 1 is smaller than Q, is smaller than P, is smaller than infinity. So this is also, there is a characterization, but the characterization is quite different. Okay, let's see. Maybe I even need more space. Yeah, so the characterization is in terms of the versions of the Wolf potentials as we saw in the previous talk. So I will continue from there. So it's equivalent to case A, lambda sigma. There is a Wolf potential that depends more or less on all the relevant parameters. Maybe I should once write down the formula, even if it appeared in the actually maybe let me, it's an integral over Q, 1 over sigma Q, and then there is a sum of the subcubes integrated with respect to this other measure omega, taking to the power p prime minus 1 times sigma q times the indicator of q. So this is the Wolf potential, and now I only wrote the formula. The condition, the characterizing condition is that this expression here should belong to a certain, I need to define this exponent R. This should belong to the certain LP space. Okay, maybe R is defined in this way, and it's a between 1 and infinity under these assumptions that Q is smaller than P. So, okay, so this is a characterization provided that in addition the coefficient sequence satisfies certain regularity. And the certain regularity is that this expression that appears here is essentially constant on Q. So this is a function, but a non-negative function, the infimum should be comparable to the supremum on each cube, uniformly over all cubes. So this is a result by Cascante, Ortega, Verbitsky. There are at least 2 papers, 2004 and 2006, and I think in the latter paper they even allow Q. I mean, Q is allowed to be, as long as P is in the reflexive range, Q is allowed to go down to 0. So this is a first characterization. So it's a characterization given that we know already a priori something about the structure of the coefficient sequence. And now, quite recently, there has been a different characterization, which is an unconditional characterization in that you don't need to assume anything a priori from the sequence. So it's the same. P prime. So this should be there, and then there is a sort of like a dual testing condition. You define the Wolf potential, it has the same coefficient sequence, but you reverse the rows of sigma and omega, and somehow reverse the rows of the exponents and the dual exponents in the correct way. So instead of P prime, you have Q, and also here the R stays the same, and here you get sigma. Yeah, maybe it's good to observe that this one is also, the R is somehow the invariant independent of which way you consider your inequality. For any sequence lambda. And this is a rather more recent result of Tanaka. It's probably not quite from the last year, but it already appeared in a journal in the last year. Okay, so this is, so in some sense the situation is, the boundedness of these operators is completely understood, but also the characterizing conditions look completely different depending on the relative size of P and Q. And maybe so the main result that I want to, or the main result with some contribution from my part, is to provide kind of like an alternative point of view into these two regimes, which kind of possibly unifies the picture a little bit. But maybe before that, I would like to make another little comment. Actually, before the conference, and especially during the time that I was supposed to give the title and abstract, which I a little bit delayed. So I was kind of hoping to be. So notice that here in these results, you are allowed to enter the Carlton zone, and I was somehow hoping that I could also say something more about this one, but unfortunately there is nothing new that I can provide about this region. So it's now it's still an open, a little open problem here would be to somehow to try to obtain a characterization for this full range of exponents without making any assumptions of lambda. So if you know a little bit little bit of the sequence lambda beforehand, then you can obtain a characterization in a large range of exponents than if you just start with the general lambda. So there is an open question. So this is open for general lambda. And this I cannot answer at the moment. But what I can say a little bit about is somehow, or try to provide an alternative characterization which looks a little bit more unified in the two cases. So here somehow, let's say if let's say you keep P fixed and let your Q approach P from below, so it's somehow, in a way you would expect that the characterization should somehow converge to the other characterization, but this does not really happen in any obvious sense. Okay, so now the alternative characterization, which is by, okay, it's somehow th times 2, so it's one of them is myself and the other one is my student who happens to have the same initials, and then with Kang Wei Lee, who was visiting us for 2 months last year. So the other is my student and the other one is myself. So now again the same boundedness question for these operators. It holds if and only if the following. So this is not exactly R-boundedness, but this is maybe a little bit in the spirit that you take some kind of a sequential version of boundedness. So now I begin by just rewriting the testing condition in a little bit different way. I basically divide everything on the left-hand side so that this one, so the old testing condition should simply be that this one should remain uniformly bounded over all cubes. But now I do something slightly more complicated. I take a family of cubes and I take a little LR norm of this one. And I require that this one should be uniformly bounded over all. Okay, I need to check sigma sparse collections F of dyadic cubes. And what does this mean? The sigma sparse, it's a little bit more general than being disjoint. So I'm asking that for all Q in F, there exists some subset with two things. First of all, these EQs are pairwise disjoint. And the second thing is that the EQ measured in terms of the sigma measure should be a substantial portion of the original. And once again, I will need the dual condition for the rows of the exponents and the measures reversed. And EQ is so this condition should hold for all families which are sigma sparse, and to be sigma sparse means that for every cube in my collection I have some subset, and these subsets are pairwise disjoint but have a substantial portion of the original one. So yeah, maybe So a very basic example would be, for example, that I have a cube and this one, and this one, and this one. So clearly they are not disjoint, so this would be, let's say, my Q1, but I could take this one as EQ1. So this is my Q2, Q3, this would be my EQ2, and so on. So each EQ is a substantial portion, in this case exactly 1/2 of the original one, and the EQs are pairwise disjoint. The original cubes need not be. So this is the condition of sparseness, and I require that this one holds for all sparse collections. Okay, so, and the exponent R, well, the R is actually exactly what it was before, except that maybe I should add that now it's the maximum of what it was before and 0, so 1/infinity. So in the case that, so this is actually this is just the same condition. There is nothing new in the result of Sawyer. It's just rephrased in a different way because the L infinity norm simply means that these quantities should stay uniformly bounded. But in the other regime, I have a different characterization which somehow has a natural limit to the condition in the, yeah, so now if Q approaches P, this one approaches 0, which is 1/infinity, so I just recover the other condition. Okay, so it's quite legitimate to wonder what's the usefulness of this condition. So okay, it provides a certain unification that at least you can see that the one characterization converges to the other one. Of course, it's quite questionable whether there is any other benefit of this condition over the Wolf potential type characterization. But maybe there is at least somehow one conceptual advantage that I can offer you to sell this possibly complicated looking condition. The fact is that somehow, okay, actually maybe I can tell you 2 reasons. One reason is that in this characterization, both implications in the equivalence are non-trivial results. So in this result, only the implication to this direction is something non-trivial. The other one is something completely obvious, which has nothing to do with the structure of the operator. It's true for any operator. You just substitute some functions. On the other hand, in the other one, I don't know. I mean, maybe to some of you it's obvious, but in any case, not to me, that it's somehow not immediate just by staring at the formula why the boundedness of the operator would imply the membership of the Wolf potential in this one. So somehow both directions are non-trivial results, and they use the specific structure of the operator. So here, at least one advantage of the characterization is that okay, I mean, I'm not expecting that you see immediately why the boundedness implies this sort of sequential boundedness, but it turns out that it's somehow this implication is maybe 1 degree more elementary. I don't think it's probably not true for, I don't know actually if it's true. Probably I assume it's not true for general linear operators, but it is true sort of if I have an operator T which is positive in the lattice sense, linear and bounded from LP to LQ, then it automatically satisfies this kind of a sequential boundedness. So so this implication does not refer to the specific structure of the operator. It's just about positive linear operators. So it's only in a way, in the spirit, how the testing condition should be, that one direction is sort of essentially trivial and only the other direction requires some work. And so this is maybe one reason, one way of trying to sell the condition. The other one is that perhaps some of the concepts that went into the proof helped us see something in a situation which was previously not characterized at all. So maybe 2b is positive bilinear operators. And now so now I have an operator which takes each two functions so it's basically it's kind of like the natural generalization of the previous one. I take integrals. Sorry, this was supposed to be the lambda, and this is the indicator. Take the product of two integrals, and then I form the similar kind of object. And again, the question is whether this one maps LP of sigma 1 times LP of sigma 2 to some LQ of omega. Maybe I could call it sigma 3 in this case. And if I denote by P3, again I'm in the reflexive, everything I know about this is in the reflexive case, so P3 is the dual exponent. So this was previously characterized. So if okay, maybe I need to. So if the exponents satisfy this condition for all I not equal to j, so then this bilinear boundedness was also characterized in terms of testing conditions by Lee and Sun. And under slightly weaker condition, that if the sum of all three reciprocals is bigger than 1, there was still a characterization, again by the same Tanaka. All these are very recent from the last couple of years. So Tanaka characterized this situation, and in this case the characterization required kind of like a mixture of testing and of testing conditions and potential conditions. But until recently, this case remained open. But now but somehow the fact that the unified characterization, well, actually there was kind of like a conjecture by Tanaka of what you should need in this case. So he conjectured that somehow you would need a new kind of a Wolf potential which takes into account all the three measures at the same time, but this was sort of on a relatively vague level. He didn't put down a formula, he just said that something like this would be needed. And with one new thing that the unified framework gave us is that it gave us kind of like a way of guessing the new Wolf potential and to obtain, in the bilinear case, a characterization also for this last remaining case. And maybe the last thing, I was lucky to, on the lunch break, I quickly looked at today's archive posting, and it turned out that it looks like our framework is quite flexible because there was just today there was a new paper by Tanaka in which he pushes everything to the multilinear case with arbitrarily many components. So I was able to report on something recent enough. Thank you.
So you now consider the positive dyadic case. Can you say something about general positive operators?
Well, we actually have some, yeah. I mean, these are fairly, the positive dyadic operators are fairly good models for fractional integrals, as was also indicated in the previous talk. So it immediately one gets some new, and okay, so in the linear case, basically just another point of view into existing results for two-weight inequalities for fractional integrals, but I guess at least in this bilinear case and in this regime of the exponents, so there is a characterization of kind of a level, okay, then it's a three-weight inequality for a bilinear fractional integral operator. And so for some operators you can directly deduce something from the dyadic case. We didn't really look further. I mean, in other cases, it is kind of like a model of what you can expect, but you cannot immediately get it as a corollary. But this is for the fractional integral case, you immediately get some results.
More questions?
Have you thought about regular operators, dyadic regular operators, so that can be approximated by difference of positive operators?
No, I didn't specifically consider this case, so I don't know if more can be said about this one than for, no.
Any other comment or question?
Yes, this is just about the very last thing you talked about. So maybe it's in Tanaka's paper from lunch, I don't know. But for bilinear operators, it could be maybe natural to consider couples of dyadic intervals, that is, integral of f1 over q and of f2 over some q prime, and consider the corresponding sets with lambda q, q prime. Is there a good reason for not considering such bilinear forms?
Well, I guess for the moment, the main reason is that everything is relatively recent. So this was basically the simplest model case to understand. Actually, at least in the linear case, I have both a characterization and an application for this. So now I talked only about these dyadic models today, but these are somehow the purpose is to then use them as steps towards some more complicated operators. And in particular, it's maybe interesting to note that so here, so suppose that for every cube Q, you have two distinguished child cubes, Q plus and Q minus, no matter how they exactly are defined. So then this is a slightly kind of a positive operator of one level more complication. And for these ones, the two-weight inequalities can also be characterized essentially in similar terms. And this is contained in my paper on the two-weight Hilbert transform for general measures. And so it's a kind of like one of the intermediate propositions, and it's applied to the, although only in the case P equals Q equals 2. So I don't know about the potential type characterization but probably it can be done.
Yeah, I think you had a question.
I just wanted to say that your alternative characterization, if one of the measures is Lebesgue measure, like here omega, but by duality you can switch them, then this looks like Mazia-Netrusov's capacity characterization, and which is equivalent to the Wolf potential characterization. They use capacities, but such quotients could be expressed exactly in terms of that functions that they use.
Okay, thanks for the remark. Yeah, it may be interesting to see if there is more about it.
I think this is true. And also, well, it's a result of myself and Cascanti-Arteaga that you mentioned, this DLBO condition is not needed if, say, one of the measures is nice, if it is Lebesgue measure, right? And then there was this question in the book by Adams and Hedberg, how to define a Wolf potential, and I think that answered that question. But this gives a two-weight version of those results.
Thanks.
Okay, so I think we can thank Tuomas again.